Hey guys, we are going to wrap up thermochemistry today. We'll talk about Hess's law as well as bond enthalpy, really finding the enthalpy of a reaction. First off, what we want to do is we want to discuss enthalpy of formation. A couple key points to enthalpy of formation. The first is we have to understand that a formation value always requires that we have 1 mole of products created in this chemical reaction. The second criteria that has to be met is that it always has to come from the elements in their standard states. So if you recall that elements in standard states, we could be talking about a diatomic element, typically gases. We could be talking about a metal, an individual atom of a metal in its solid state. But you always have elements in their solid states as a beginning point. So one example of this could be you have carbon used in, let's say, propane, so C3H8. And we want to talk about the formation of this propane. Well, we notice that it comes from 2 different atoms. We have carbon and hydrogen. So our standard state carbon is going to be its solid, and specifically the graphite form, not the diamond form, the graphite. That's going to be combining then with hydrogen, and since hydrogen is a diatomic element, that's going to be H2. In its standard state here, we know that that's going to be a gas. So when it comes together, we balance this, and we're going to see that there must be 3 carbon, and then we see there would be 4 of our hydrogen gas in order to make 1 mole of our product. Now, one unique thing that you do have to kind of watch out for in these types of problems is we actually can end up with fractional partial values, okay? So let's say that instead of this formation equation, let's say that we're going to make some carbon dioxide, CO2. The carbon dioxide has to come from carbon again in its solid state, but it also comes from oxygen. That oxygen gas is shown here. So this one works out the same way. It's going to be 1 and 1, making 1. Let's say that it was instead water. Okay, so if I try water out, that's going to be H2O as a final piece, right? Water, though, is going to come from hydrogen and oxygen. So we have H2 in the gas phase, and we also have O2 in the gas phase. The problem that we're going to run across in this case, though, is you need to have 1 H2O. With hydrogen, that's really easy, the 1 H2. But on oxygen, since it's diatomic, the only way that I'm going to get to 1 oxygen as a product is by using half of a mole of my O2 gas. So you can use these fractional coefficients, and they'll still work out with this problem. Now, what we want to look at is consider once again elements in their standard states. They're not going to have any amount of energy required to make them. If I only looked at oxygen as the thing that I'm forming, well, the standard state is O2 gas, and there's no energy requirement for oxygen to become itself. So remember that any elements that are uncombined, things that are alone, require no energy in order to form. So I have a table here, a listing of some different common substances. We're going to be turning back to this and using some of these values as we go through. But once again, we look here at the water that we talked about. In order to make H2O as a liquid, it's going to come from the hydrogen and the oxygen, 1 hydrogen, 1/2 of an oxygen. And the energy piece would be negative 286 kilojoules per mole. So this is saying, once again, if it's negative, it's releasing 286 kilojoules as 1 mole of the water is formed. Now, Hess's law is essentially a way of looking at change, the change in energy as I go from the beginning to the end. If you recall that we looked at change before in another context, let's say our temperature change, our delta T value, that would come from a final temperature subtracted away an initial temperature. Well, this is very similar. We're looking at the energy to make the products and subtracting the energy to make the reactants. products being the final, reactants being the initial condition. So if we look at some of these different values, what we're going to do is we're going to see that we can make, let's say, start off here. We're going to make water and carbon dioxide as we burn our CH3OH, our methanol in its liquid state, combining with oxygen. So what I'll need to do is first identify each of the components. I've got the methanol, and if I look to the chart, I can see that my methanol is listed right here. I get negative 239 kilojoules per mole as I form methanol from its components. So negative 239 would be 1 mole of methanol. On the oxygen, remember that this is an element, it's uncombined, so this is going to be 0. We look for water next, and the water was negative 286, so we'll go ahead and post that on there as well. And then carbon dioxide. The carbon dioxide is shown at negative 394 on our table here. So I have all of my values. Now we have to consider that we don't just have 1 mole of these things. For my methanol, there are 2 moles. So if I'm producing 2 moles, it's going to be twice as much energy. So I'll multiply the negative 239 times 2. Doing that gets me to negative 478. On the oxygen, it's 0 times anything is 0, so we'll leave that alone. And then we have water is going to be 4 times the negative 286, getting us negative 1144 kilojoules. Now we have carbon dioxide, and we'll double that. It's going to be negative 394 times 2, gets negative 788. So this is the area that confuses most of my students, is remembering that you have to do the sum, that's the summation symbol, this capital sigma, the sum of all product energies minus the sum of all reactant energies. So when you set this up, the product energies are shown here. The reactant energies are going to be shown over on the right. So negative 1144 plus negative 788, we're going to combine those two values. On the right side, we would have the negative 478 and 0, which is just negative 478. Combining these in your calculator, we find negative 1454 kilojoules per mole of this reaction taking place is going to come out as the energy given. Now, try not to be too confused by this. That is per mole of standard reaction. This is just so that we can use this to do a comparison now. So this being a negative, I could write in on the product side 1454 kilojoules as the amount of energy given off as this reaction takes place. Right? Now, we have a couple exercises that you're going to have to go through. I will let you work them out, but I'll give you the answer so that you can check your work. For this problem, we're going to get negative 2,677. So again, the unit of this enthalpy value is kilojoules per mole of reaction. Now for exercise 9, once again, take the time to work through this. I'll give you the answer to check. It is going to be negative 1,276 kilojoules per mole reaction. Final reaction here. After you've checked, or after you've worked this problem out, we'll let you check it. You should end up with negative 850 kilojoules per mole reaction in this case. Now, it's going to be really important that we remember this idea that enthalpy is one of our state functions. Enthalpy is a state function, meaning that it doesn't matter how you get from point A to point B. All that matters is the difference between the two positions, those 2 points. So an example on this, all right? So let's say I want to go from point A down here to point B. I could take a direct route, and let's say that that is a 100-mile path. Well, I could also deviate over to point C, jump down to point D, and then cross back. Now, this path is longer overall, right? Say it was 50, and then 100, and then 50 more. Well, I've traveled a total distance that's much greater. However, I still went from point A to point B, and if I measure the distance from my starting point to my ending point, it's the same. The root didn't matter. It's important that we get that idea. The root doesn't matter. You can look at multiple different things and combine those steps in order to get one overall change. Now, we can combine chemical equations in a similar way. Just like we said, we could go from point A, C, D, back to B. Well, we can do that. We can combine these stages, these steps, in order to figure out the A to B path. So to begin these, what we first have to do is we have to identify what the target equation is, really. You've got to know what you're going for, the target equation, and look at all the sub-equations and see how they could be modified or manipulated in order to add up to one overall equation. You might need to reverse an equation. So if you have an equation that runs in the forward direction, reactants going to products, let's say that it was an exothermic process, so that's a negative delta H. If I were to reverse this process, you would rewrite it so that those products now should be shown on the left side as reactants, and the reactants are flipped to become products. Doing that, the products become reactants, and the sign changes on your thermicity here. It's going to be a positive delta H now as I reverse the equation. Another thing that we commonly have to do is we have to multiply through a coefficient so that the number of things in the sub-equation match that of the target equation. Anytime you do this, you would just multiply in front of every single substance present, and you would also multiply by the enthalpy value. So if I had, once again, R going to P, and what I do with this is, let's say, again, I have a negative delta H value. If I wanted to triple the value, you would have to go 3 times R, 3 times P, and 3 times the enthalpy value. Okay, so that's how we approach those. And finally, at the very end, you need to double check that everything cancels out appropriately so that the sum of the sub-equations is the same as your target equation. Now, I will go through an example of this so that you have a clear idea of how this works. In our equation here, we have exercise 11. What we'll do is we're going to break it down. We want to fully flesh this out. And because it's going to be a little bit easier for me, I'm going to jump out of my presentation and jump here. We're going to look once again here at exercise 11. Now, we have a lot of information that's presented. We know that the target equation shown up here, the goal, and then all of these are my sub-equations down on the bottom. What you want to specifically do is look here at each of the components of the target. This H3BO3, we want to see where is that in my equations, these sub-equations below. It's a reactant in the target equation, and we find it as a reactant here in one of my sub-equations. There is an issue though. My target equation that we're looking for has a 2 coefficient. That 2 means I'm going to have to double the sub-equation in order to make that work. So I will write this in as 2, 2, and 2, and then my energy value is also going to be times 2. So doing this very quickly, we're going to get negative 0.04 kilojoules per mole reaction on there. What I'll do at this point now is look to the other components. B2O3 solid. I need some B2O3 solid. And looking at all of my other sub-equations, I find there is B2O3 solid right here. You will notice, however, that again, the coefficients don't work. What I need to do is I need to modify my sub-equation so that my 2 B2O3 become 1. To do that, I can just divide everything by 2 in order to make that work. So this becomes half of an H2B407. 2 divided by 2 is going to become 1. And then this will also be a 1/2 on the water. I'm going to have to take my 17.5 and I'll have to divide by 2 on that as well. So this should come out to at 8.75, I believe, positive 8.75 kilojoules per mole reaction, right? Now, the last thing that we have to check, you've got to verify this final piece, which is water, H2O. Well, when I look at it, I see that there's H2O shown up here on the right, and there's also H2O shown on the left. And we know that those two things would cancel each other out. We don't want them to cancel, we want them to add up to being 3 waters. Oh, and there's another water down here. I have another half an H2O. So we've got an issue with that H2O. What we're going to have to do here is we're going to have to reverse this. We're going to have to flip this equation over so that I can get water as a product and not as a reactant. I don't want it to cancel here. You'll also see we have a secondary item, H2B407 and H2B407. That item is on the left side, both on the left side, but it's not part of the target equation. By reversing this middle equation, I'm able to fix that problem too. So let's go ahead and work that out. I'm going to rewrite this as HbO2 for HbO2 on the left side. That should turn into the H2B407 and H2O. The energy, when I do this, has to be flipped in terms of its sign. So my delta H is now going to be positive 11.3 kilojoules per mole of reaction. I'm going to cross this off on top just so I don't confuse myself as I want to add these up. But I'm not completely out of the woods yet. I have the H2B407 on the left and on the right. We have one more substance that we have to pay attention to. What we're going to do is we're going to see this HbO2 is not part of the target equation. But now notice I have it on the left and the right, so it would cancel out. The problem that we still have to deal with is the coefficients in this second equation. If I were to combine this, 4 HbO2 on the left and 2 on the right, they won't cancel out. If I were to combine my H2B407s, it's 1/2 on the left and 1 on the right. Those don't cancel out either. Finally, that H2O, if I were to add all my H2Os right now, I get 2 and 1 and 1/2 is 3.5, where I need to get to 3. We can fix this by multiplying 1/2 or dividing 2 once again through this equation. So dividing by 2, this 4/2 becomes 2. And now that'll fix the HbO2 problem. I will have 1/2 on the H2B407. That'll fix that problem. And finally, I get a 1/2 here, and I update my total by dividing by 2 on that. Okay? So breaking that down also in terms of the math, it should give me, what is that, 5.65, and that's a positive now, 65 kilojoules per mole reaction. Now, the final piece of this puzzle is we do have to double check that the two sides combine to make our target equation. As I combine the sides, we'll notice that H2B407 on the left and on the right, it's the same number. Those will cancel out, so I can cross them off. Also here, my HbO2s, it's 2 on the left, 2 on the right, so combining those, they cancel out. And the final piece is looking at my waters. I have 2 water, 1/2, 1/2, but they're on the same side. That ends up being 3 H2O as a product side. The other things that are present and don't cancel out would be that H3BO3, 2 H3BO3. We also see we have our B2O3, and one of those exists, B2O3. Now when I compare the two, we notice that the target equation in each case matches exactly my combined equation. Since I've confirmed that my equations cancel out properly, what I do now is I add up the energies. By adding up the energies, we're going to see we have 8.75, 5.65, and negative 0.04. when combined and rounded appropriately, we should get 14.4 kilojoules per mole reaction. So hoping that made some sense. We're going to go ahead and move back now into our slides and work the next part out. What we have to also understand outside of Hess's law in this combined form is we have to understand that we could also approach it not from the stoichiometry perspective, but from a bonding perspective. Recall that anytime energy is added or absorbed by a compound, it would break bonds that would overcome attractions between particles. And you can have several different forms of this. You also can overcome intermolecular attractions. When we're dealing with bond energies, we're primarily focused on covalent compounds. So we're looking at a nonmetal to a nonmetal where they're sharing electrons. If we're forming bonds, recall that forming bonds makes these things more stable. And by making them more stable, what will end up happening is a reduction in their potential energy. Energy has to be given off in that process. So if I show the basic breakdown here, it's the sum of all broken bond energies minus the sum of all formed bond energies gets me to my change in energy overall. We'll look at this exercise as well, just to help break down this concept, this idea. Let's go ahead, jump back here into OneNote, just it'll be a little bit easier to show that work and break it down. Now, as I start, what I want you to do is I want you to think about the structure of these things. You should recall from last year, we've done Lewis structures, which is the way to show the bonds as molecules are formed. So we're showing that there are 3 different bond types present with bond energy values that go with them. What I want to do is I want to draw the full Lewis structures to show what's happening, all of the bonds that are present in this reaction. I have hydrogen bound to another hydrogen in the H2 molecule, and I know that has an energy of 432 kilojoules per mole of those bonds that would form or break. Next, we have our fluorine gas. That's one fluorine with a single bond to another fluorine. The energy component here would be 154 kilojoules per mole. Now, there are a couple things that we can note on that. The bond that holds hydrogen together must be stronger than the bond holding fluorine together, since there's a larger amount of kilojoules per mole to form or break the bond. Lastly, we're going to look at bond one hydrogen bound to fluorine. This connection, we're going to see, will take 565 kilojoules per mole in order to form or break. But looking here, you'll notice that we don't have one of these. We actually have 2 bound together. So if I want to figure out the total amount of energy change, what I've got to do is I've got to figure out the sum of energies, the product energy. Think about this, as products form, they're more stable, so that's a positive energy. As reverse that, products forming becomes more stable and gives off energy. The reactants that are breaking, that's where we absorb energy, and that overcomes the forces that hold them together. So recall that our reactants here, what I have to do with those is I have to add those energies up. They're going to be positive in order to break bonds. And then on my products, I have to take those values and I have to write them as negative because they're giving off energy as we form bonds. So working that out, what we're going to see is 565 times 2. That should give me, what's that? 1130 kilojoules. That is the amount of energy that it takes to form bonds. It'll be a negative because energy is released. Now on the opposite side, we combine these two. We are going to have 6, 8, and 586 positive, the energy there, in order to cause those to get broken. Combining these two, your products, negative 1130, and your reactants, 586. When I combine the two energies, I should end up with negative 544 kilojoules per mole. So that's what we have for today. Let's go ahead and stop there and resume this moving forward.